This demonstration video will show you how to do PCIe Gen 6 RxLEQ tests on the MP1900A. First, let's look at the module configuration. We have the clock synthesizer module in slots 1 to 2, the jitter module in slots 3 to 4, the redriver in slot 5, the PAM4ED in slot 6, the PAM4PPG in slot 7, and finally the noise module in slot 8. Make the necessary intermodule connections as seen in the diagram. These are the required module and software options. Next, let's move on to the test preparations. Launch the MX1900A software and select BERT for PCIe 1 to 6. Also launch MX1900A. Ensure that the module FPGA and firmware are updated. Once the main application has finished launching, switch to the MX1900A screen and start the PCIe Link Training application. Click on Start Search and Connect. Click on File and initialize the parameters of both applications. After initialization, click on Operate MP1900A and move to the redriver screen. Turn the CTLE2 on and return to MX1900A. Now let's start the RxLEQ test. For an add-in card DUT, follow the diagram and make the necessary connections. Note that the real-time oscilloscope is optional during the RxLEQ test. This is the connection diagram for a system DUT. Let's check how Link Training works for PCIe 5. For this demonstration video, we will use an add-in card DUT. With the LEQ test set to RxLEQ, click Apply. Click on the Option button to select the appropriate CBB controller settings and start Link Training. We achieved loopback active at the Gen 5 data rate. Click on the LTSSM log button to display the Link Training state transitions. Adjust the delay as needed to achieve the optimal bit error rate. Now, let's try Link Training at the Gen 6 data rate. For RxLEQ, presets from Q0 to Q10 can be set as the PPG starting preset and DUT initial and target preset. In the More Results tab, Gen 6 information such as 1B1B control skip, SRS clocking, and Flit mode supported bit can be displayed after Link Training. In the Option tab, 1B1B skip interval settings, fine-tuning of link equalization presets, redriver CTLE, and AUX trigger output can be adjusted if necessary. For the Gen 6 PAM4 signal, in order to optimize the redriver and ED parameters such as threshold voltage, delay, and CTLE, perform return path optimization. This method uses the compliance mode of the PCIe device to instruct it to generate Gen 6 compliance patterns with the different presets. The compliance mode toggle signal will come from the MP1900A TX. Select the DUT initialization method. In this demo, we'll use the CBB controller. Select the auto reset method. Next, select the presets for optimization. And click on Start Optimization. The MP1900A will start putting the DUT in Gen 6 compliance mode for the selected presets. Using the DUT signals, the MP1900A Rx parameters will be automatically optimized. We can see the optimal parameters, along with the resulting bit error rate in the table. This process will be repeated for each selected preset. After the optimization finishes, the best BER and preset combination will be displayed. Click on Close to proceed. Change the RxLEQ settings if necessary and click Apply. Note that you can add the necessary jitter and noise through the Configure tab or by clicking on Operate MP1900A. Then, start Link Training. We achieved loopback in Gen 6. Click on the LTSSM log for the state transitions and equalization information. We can see that the MP1900A requested Q0 and then Q1 as set in the RxLEQ tab. To measure BER, click on Configure and start Auto Search for delay. In this example, we achieved an FBER of about 2E-11. Let's start a BER measurement. The DUT passed because its FBER is less than 1E-6. We can also perform jitter tolerance tests on the Run Test tab. Adjust the test parameters on this screen. Open the JTLL settings screen for detection, auto search, jitter step, and timer parameters. If the settings are good, click on Run Test. This will automatically start an auto search if selected. Click on the Detail button to see the test progress. After the test finishes, you can access the Graph tab and also generate an HTML or CSV report file. The MP1900A also has helpful and convenient functions for Flit FEC debugging. The test pattern can be changed to Flit data. The PAM4 PPG has a new feature to insert PCIe 6 FEC symbol errors. The PAM4ED has a FEC error distribution graph and a FEC capture function. Let's try adding FEC symbol errors from the PAM4 PPG. Also, let's set the PAM4ED capture conditions to trigger according to the inserted errors. Turn error addition to on, and then start capture. We can see that errors are added every 8 bits, not distinguishing between ECC groups, as set in the Error Addition tab. Next, let's try adding errors every 24 bits, which will add them to one ECC group. This can be seen in the capture data. The FEC Error Distribution tab provides real-time results with graphs versus Flit and ECC group. Detailed results of the BER, FBER, and Flit errors can also be accessed in real time. In summary, we were able to perform PCIe Gen 6 RxLEQ tests on the MP1900A with return path optimization, convenient FEC debugging functions like error addition and Flit capture, and detailed BER and FBER measurements. This concludes the demonstration video. Thank you for watching.